In this video, we'll continue to talk about two more proof methods: proof by contradiction and proof by cases. The third proof method is proof by contradiction. Now let's look at the simple form of theorems. So we assume we just want to prove S to be true. Now, what we can do is, suppose you can find a contradiction C such that you can prove this implication is true. You can see the hypothesis of this implication is not S. Why do we create such an implication? The reason is because C is a contradiction. We know C must be false. However, you proved this implication is true, and by the truth table of implication, we know that the only way that this implication is true when the conclusion is false is the hypothesis is false as well. And since the hypothesis is not S, and not S must be false, therefore S must be true. Then some of you may ask why we do not prove S to be true directly instead of going through all this long route to prove another implication to be true. The reason is sometimes it's not easy to show S is true directly, and it may be easier to derive some contradiction from not S. That is proof by contradiction. Let's see one example. We want proof that the square root of 2 is not a rational number, or in other words, is irrational. From the previous example for proof by contraposition, we know that if you know a number is irrational, we don't know how to represent it. Okay, so now what we are going to do is we are going to use proof by contradiction. So we are going to assume not S is true. Here, this is S. Then we'll try to derive some contradiction, C. We're going to assume not S is true, which is the square root of 2 is rational. What's next? Because the square root of 2 is rational, by definition, we know it's equal to P over Q, where P and Q are both integers and Q is not equal to 0. And in addition, P and Q should not have any common factors. This is very important. Keep that in mind. And then we can take the squared operation on both sides of the equation. We'll have P squared equals 2 times Q squared. Because Q is an integer, Q squared is an integer. Then you can see P squared is basically equal to 2 times an integer. Does this look familiar? By definition, that means P squared is even. And if you recall the first example for proof by contraposition, if P squared is even, we can conclude P is even as well. Now, by definition of even numbers, we know that since P is even, P is equal to 2 times K, where K is some integer. Now, let's substitute P equals 2K back into this equation. You have 2K squared equals 2Q squared. Then you can cancel 2 on both sides. You have Q squared equals 2K squared. Therefore, Q squared is even. And now let's use the theorem that if Q squared is even, Q must be even. This is from the first example for proof by contraposition. Now look what we have concluded. P is even, Q is even. Therefore, we prove that 2 is a common factor of P and Q. Do you see the contradiction? Previously, we assume P and Q should not have any common factors. But now we prove that they do have a common factor. Therefore, these two are negation of each other. And since you proved both of them are true, let's say this is R, this would be not R. So you proved R and not R is true. That is a contradiction. Therefore, since you proved not as implies a contradiction is true, we know that by the truth table of the implication, not as must be false. Therefore, as must be true. Okay? To summarize, if we initially want to prove a theorem S to be true, if direct proof does not work, what you can do is you can prove not as implies a contradiction is true in order to prove S to be true. Now let's look at the case where the theorem itself is of implication form. This basically is saying now S becomes P implies Q. Let's see how to use proof by contradiction. Same as the simple form. If you can just think of this as S, remember we want proof not S implies a contradiction. Here I just use F to denote it's a contradiction instead of the letter C I used previously. What is S? S is just P implies Q. We want to prove this implication is true. And in order to prove this implication, since there is this implication inside the hypothesis, we can apply the implication law to transform implication. Okay, so step 1, using implication law, this is not P or Q implies F. And then you can apply De Morgan's law. Now the hypothesis becomes P and not Q. So now you can see the new implication is completely different from the initial implication because we use proof by contradiction. So in general, what we are going to do next is you're going to start from the two premises in the hypothesis. Then you try to derive a contradiction. But now you may ask, how do we find the contradiction? Well, there are 3 ways of finding a contradiction. The first way is if you can imply Q from P and not Q, then of course Q and not Q is a contradiction. Second, which is similar, if you can imply not P is true, then since in your premise you already have P is true, P and not P is also a contradiction. Third one, if during the proof you are able to prove R is true and not R is true, then R and not R must be a contradiction. The third one is usually the hardest one because this R seemingly comes from nowhere. But we're going to see some examples on how we can derive a contradiction using the third method. First example, If 3n plus 2 is odd for integer n, then n is odd. You may have noticed this is exactly one of the examples for proof by contraposition. But now let's see how we can use proof by contradiction to prove this theorem. By the way, for a theorem, there could be multiple ways to prove it. In other words, the proof is not unique, just like this one. In order to use proof by contradiction, we are going to assume P and not Q are both true, then imply some contradiction. What is P? P is 3n plus 2 is odd. What is Q? Q is n is odd. Therefore, not Q is n is even. So these are the two premises we currently can assume to be true. Let's see how we can derive a contradiction. Since n is even, we know n is equal to 2 times k, where k is some integer. Then let's substitute n equals 2k into 3n plus 2. It's equal to 6k plus 2. And if you factor out 2, you have 2 times 3k plus 1. What does this mean? This means 3n plus 2 is even. This is essentially not P. And one of your premises is P is true. Therefore, P and not P is a contradiction. Many of you may notice that if an implication form theorem can be proved using proof by contraposition, then you must be able to prove it using proof by contradiction. Why? Because you prove not Q implies not P. And in proof by contradiction, one of your premise is not Q. Therefore, you should be able to prove from not Q to not P. Then, of course, the other premise is P, and you have these two together as the contradiction. Second example, if a number added to itself gives itself, then the number must be 0. Of course, again, there are other ways to prove this theorem. But now I want to show you how to prove this using proof by contradiction. First, identify this is P and this is Q. For proof by contradiction, we assume P and not Q are both true. P is this one, but we want to represent P using mathematical statement. It means x plus x equals x. What about not Q? Not Q is x is not equal to 0. How do we derive a contradiction? Well, for the first premise, we can simplify it to 2x equals x. And now there are two ways to derive a contradiction. The first way is you can subtract x from both sides, then you're going to have x equals 0. What's this one? This one is Q. However, you assume not Q is true, but now you imply Q is true. So this two is a contradiction. So this is the first method. Second method is, since 2x equals x, and in addition, we know x is not equal to 0. So what other operations can we do on both sides of the equation? Yes, division. If you divide both sides by x, you're going to conclude 2 equals 1. And if you consider this as r, then as the common sense, or we call it axiom, we know that 2 is not equal to 1, which we can consider this as not R. So you can see we derived R and not R. That is exactly the third way we can find a contradiction in general. Okay? But either way, as long as you can derive a contradiction, you are basically proving the original implication is true. Here is an exercise you can work on after you watch all the videos. Last proof methods, proof by cases. Again, we're going to focus on the implication form. P implies Q. But now let's assume P is equivalent to P1 or P2 or all the way through Pn. And therefore, instead of proving the original implication, it's equivalent to prove this one. Basically, we prove n implications to be true now. Why can we do that? We can show this is equivalent to the original implication. Let's see how. Because P is equivalent to this one, we can just put this long hypothesis in the original implication. Then we can apply implication law on the whole implication. So you have this one. And look at this part. You can apply De Morgan's law. So you distribute this negation inside the parentheses. But don't forget to change the connective from or to and. Now, the connectives inside are different from the one outside. You can use distributive law to distribute or Q into the parentheses. You have those ones. And for each of the ors, you can apply the implication law again to transform that into an implication. Okay? So now you compare these two sides. We show that these two are equivalent. Therefore, we can just prove each of the implications to be true individually. Then you can conclude the end of them is true. And thus, you are equivalently proving the original implication is true. I know some of you may ask, initially, we only need to prove one implication is true, but now we have to prove multiple implications to be true. How can that make the proof easier? The reason is sometimes the original hypothesis is hard to analyze. But once you break it down into multiple cases, for each individual case, it's easier to analyze. Let's see some examples. First one, if n is even, where n is between 4 and 12, then n is the sum of two prime numbers. Do you still remember what is prime? The definition is a number is prime if it has only two factors, 1 and itself. For example, 2 is prime because it has only 1 and two factors. 3 is prime, 5 is prime, but 9 is not prime because 9 has 3 factors. Okay? Now, how are we going to prove n is the sum of two prime numbers if n is an even number and is in this range? And you already know that we're going to use proof by cases. Since n is even and n is in this range, we can just consider all the possible values of n, because n can only be equal to 4, 6, 8, 10, and 12. Only 5 values. You can see if you consider this as p, then p1 is just n equals 4, p2 is just n equals 8, and so forth. And of course, p is equivalent to P1 or P2 or all the way to P5. And we just want to prove Pi implies Q, where I is from 1 to 5. And that can be easily done. If n equals 4, then 4 is equal to 2 plus 2. And we know that 2 is a prime number. And 6 is equal to 3 plus 3. 8 equals 3 plus 5. Both are prime numbers. 10 equals 5 plus 5. Both prime numbers. 12 is equal to 5 plus 7. Both are prime numbers. So you can see we proved each of the 5 cases, and therefore we proved the original statement to be true. Second example. For any two numbers x and y, this equation is true. How do you prove it by cases? We know that to prove an equation to be true, we are going to go from one side of the equation and using a chain of equalities to connect to the other side. But in order to do that, we have to get rid of this absolute value operator. But we know that we cannot just simply remove the operators because the absolute value of a number depends on the sign of this number. And that's exactly how we're going to divide P into multiple cases. Since there are two numbers, and each number can have two signs. Either it's greater than or equal to 0 or it's less than 0. If it's less than 0, then the absolute value of x is equal to minus x. And therefore, there are 2 by 2 4 cases. Both of them are non-negative. X is non-negative, y is negative. X is negative, y is non-negative. And last one, both of them are negative. Case 1, if both of them are non-negative, we can simply remove these absolute value operators. Then we have x times y. And also because they are both non-negative, the product of these two is also non-negative. Therefore, x times y is equal to the absolute value of x times y. This is case 1. Case 2. Because x is non-negative, we can simply remove the absolute value operator. And now, since y is negative, the absolute value of y equals minus y. Then we have minus xy. Because x is non-negative, y is negative, we know x times y is non-positive. And since we have this minus sign in front of it, the minus xy is non-negative, and therefore is just equal to the absolute value of x times y. Third case, since x is negative, the absolute value of x equal to minus x, and absolute value of y is just equal to y. Then we can argue that since x is negative, y is non-positive, similar to the second case. This one is non-positive, and then since you have this minus sign in front of it, this whole value is non-negative as well, and you know it's definitely equal to the absolute value of x times y. For the last case, since both of them are negative, it's equal to minus x times minus y. And these two minus signs will cancel each other. You just have x times y. Since x and y are both negative, x times y must be positive. Then it must equal to the absolute value of x times y. Now you can see for all 4 cases, we prove that this equality holds. Therefore, we prove that the original theorem must be true. Of course, you don't have to prove the equality by showing the left side is equal to the right side. You can also go the backward direction. You can prove that the right side of the equation is equal to the left side of the equation. That's also how I showed on the slides. Here is an exercise for using proof by contradiction. You can try to prove this theorem after watching all the videos. So now we have introduced 4 basic proof methods that we can use to prove a theorem to be true. In the next video, I'm going to show you how to disprove a statement. In other words, how to show a statement is false. And what are the good strategies to write a good proof? In the last, I'm going to show you how not to prove a theorem to be true. In other words, I'm going to show you what are the common mistakes people make when proving a theorem to be true.